So, oops. Good. Sorry. Right. I'll start with some excuses and apologies. It's been a bit of a busy couple of weeks. We had the radiator in the office leaked, and so I had to spend some time sorting that out. We've got the carpet cut away and stuff like that, and we had to dismantle the PC for a few days. So I'm kind of
sorry to hear that.
So I'm kind of behind on various bits of work. So I haven't had as much time to prepare these slides as I was hoping. So the content is there more or less, and we'll have to see how well I do at talking you through it. We'll see. I'm not sure how long I'll talk for. I think the first session will be longer than the second. We'll see how it goes. Good. So and one other thing before I start is I can't see the chat at the moment. So if Marco or someone could let me know if there are any questions I should address as we're going along. That would be really helpful. Thanks.
Sure, I'll do that.
Okay, that's great. Good. So I'm here today to talk to you about aggregation. This session, I'll be talking about various kinds of things you might want to aggregate, and various limiting results that constrain how good a result you can get when you're aggregating. In the second session later this afternoon, I'll talk more about aggregating imprecise probabilities specifically. Okay, so what is aggregation? Basic idea. The other thing I should say is that this is going to be quite kind of bird's eye view, quite sort of informal, big picture kind of approach. I sent Marco a syllabus that has some sort of readings. So if you're interested in a specific aspect of this, there's a document there you can use to start your exploration of the topic. Okay, so basic idea of aggregation is you have some sort of collection of individuals, people, for example, and they have some kind of attitude, right? And we'll look at various kinds of attitude they might have. But for example, you could have, you might want to aggregate different individuals' beliefs, right? You might want to aggregate different individuals' preferences over the options available to them, for example. And what you want to do with that collection of individuals' attitudes is you want to generate some kind of group attitude. You want to aggregate the individuals' attitudes. That's better. So we're going to look at three different kinds of attitude you might want to aggregate. We're going to look at preferences, so some sort of relation over the options. Propositional knowledge, so standard just beliefs about what things are true and false, and then probabilistic information. So we'll see there's quite a lot of commonalities or similarities between these different kinds of aggregation. And then after the break, we'll see how these different methods for aggregating, or different topics of aggregation, inform the topic of how you might want to aggregate imprecise probabilities. As I said, the other thing to say here is that this session is mostly going to be about kind of negative results. You can't have all of these desirable properties of aggregation. There are going to be impossibility theorems, pretty important part of the literature on aggregation results. second half, when we're talking more about imprecise probabilities, we're going to switch to talking about sort of positive results of different methods for aggregating imprecise probabilities. So why might you want to aggregate a collection of individuals' attitudes? I think it's important to ask that question because there are several different answers, several different reasons you might have for aggregating a collection of attitudes, and depending on what reasons you have, what sort of outcome you want, it might be that some methods or others appear more attractive to you. So, for example, you might want to aggregate a collection of individuals' attitudes just to generate some kind of rough summary of the individual's views, right? Or you might want to generate some kind of opinion that serves as a kind of compromise approach, compromise attitude, with the goal of using that compromise attitude to make a decision, for example. You might think that you might sort of use the machinery of aggregation to think about what the consensus approach that a group of agents would meet after discussion. So the idea is that the aggregate opinion is supposed to be the opinion that all of the individuals converge on after after some sort of discussion allows the individuals to respond to the reasons given by each other. Another approach is you might be sort of standing outside of the group and you want to take on board the opinions of the group of agents. So you're some kind of external decision maker. You want to take into account the attitudes of the individuals. Or you might be within the group, one of the members of the group, and the aggregate view is your opinion after having learned what the others think, if you like. Right. Now, these aren't all totally distinct reasons you might have for aggregating, but the idea is that some or the other of these different reasons for aggregating might have an effect on what you take to be desirable properties of aggregation. So I think it's important, it's useful to sort of have in mind that aggregation isn't the sort of one monolithic procedure. There's different reasons you might have for aggregating. For the most part, in the remainder of these sessions, we're just going to talk about the sort of more abstract, formal ideas, and these different reasons aren't going to play much of a role. So here's the plan for the rest of this session. We're going to talk about voting, right? That's aggregating preferences. We're going to talk about judgment aggregation. That's aggregating propositional knowledge, true, false, yes, no beliefs. And then we're going to talk about probabilistic aggregation. And then there's going to be, at the end, there's going to be a sketch of a proof. And that's really the only place where we give a proof or we give anything kind of remotely formal in this half of the summer school session. It's going to be it's going to be abstract enough that the proof sketch is supposed to be sort of applicable to all of the kinds of aggregation that we've been talking about. Or we're going to sketch, the strategy of the proof, if you like. Right. Let's talk about voting. We're starting with voting because basically this is, historically where this all started, with a classic result by Kenneth Arrow called Arrow's impossibility result, from the 1950s, from 1950, I think, in fact. and it's, you know, incredibly important result, started this whole field of social choice theory, and inspired the other topics we're going to be talking about later. Okay, so here's the idea. We have a collection of individuals. Typically, we're thinking about individual people, right? They have preferences over some collection of options. Preferences represented by a relation, right? A transitive and complete relation over some collection of options. Now, those might be candidates for office, right? In terms of a classic kind of, you know, political vote, but you could be a collection of people voting about where to go for dinner, for example, right? That's another same deal, right? The options there would be the possible restaurants you could go to, you know, back when people did things like go to restaurants. And you need to come up with one answer, right? Only one of those politicians can be, you know, the member of parliament for your constituency. You can only go to one of those restaurants on a particular day, right? So you have to come up with some kind of single option that is the aggregate choice, right? So this is, you know, we're already making a kind of making a sort of formal. So we're talking about aggregating in the sense of generating a complete and transitive relation over the options, whereas in sort of real world voting, if you like, typically what happens is you're only interested in the thing at the top, right? You want the top candidate. You want to pick who's the top candidate or the top restaurant into, you know, from the perspective of the group opinion. But in the sort of formal social choice theory, when you're talking about aggregating opinions, you're generating the full relation over the options, not just the top element. We can talk more about the difference that makes later if you like. It doesn't really make much of a difference. Okay, so we want to generate a group preference, an aggregate preference ordering over the options. We want to do it in a way that, you know, has some kind of desirable properties, that has some good features, if you like, right? We want the aggregation to be fair, right? Whatever that means. We'll talk about what we mean by fairness later on. And it also should reflect the opinions of the individuals, right? That's the point, is that the group opinion is supposed to be somehow a reflection of what the individuals think about the topic. Okay, so we've got 3 individuals, right, and 3 options. The 3 individuals are an astronaut, a clown, and a vampire, and they're trying to decide what to do with their afternoon, right? And the options are: they could go and play basketball, they could go sailing, or they could go and play golf. Okay. So how are we going to aggregate the opinions of these 3 individuals? One obvious, and as we'll see, fairly naive suggestion is just to sort of do a kind of majority pairwise voting, right? So option A is preferred to option B, just in case the majority of the individuals prefer A to B. Okay? And just do that for each pair of individuals and use that to generate your ordering. Now, you may already see where this is going to go wrong. So here's the idea. In a choice between basketball and sailing, the group prefers basketball to sailing. So the arrow going up means, you know, the thing at the top is preferred. Okay. So 2 individuals, the astronaut and the vampire, prefer basketball to sailing. 1 individual, the clown, prefers sailing to basketball. So the majority of the individuals prefer basketball to sailing. So the group preference is for basketball over sailing. Okay. Now you can already perhaps see the trouble that this is going to cause you if you have the preferences of these three individuals, right? Their preferences are cyclic, right? So for each pair of options, right, two individuals prefer basketball to sailing, two individuals prefer golf to basketball, two individuals prefer sailing to golf, and so on. You have a cycle there, right? Now that seems problematic, right? Because that's not that cyclic relation is not sort of rational or useful preference relation to have. So one nice illustration of this kind of idea is, let's imagine you've got a bus going around a roundabout. There are three turnings off the roundabout, okay, and there's a third of the passengers want to take each turning. So a third want to take turning A, a third want to take turning B, a third want to take turning C. The bus is going around the roundabout. They come up to the turning A, right? And the driver says, do you want to turn off? We have a vote to decide whether to turn off the roundabout. 2/3 of the passengers say, no, we don't want to turn off the roundabout, because 2/3 of them don't want to go off at A, they want to go off at B or C. So they come around to B, the same thing happens. 2/3 say, no, we want to stay on the roundabout. So the bus just keeps going round and round the roundabout if you're dealing with these sort of pairwise choices. So that's a nice kind of example of this sort of cycle in action. Right, and another example, and it's also an example of how you can get the result you want by manipulating the agenda, right? Manipulating the things you're choosing over. But that's a separate topic we won't really have time to touch on today. Okay, so that's not great. So the problem with that method of voting, or that method of aggregating the preferences, that it generated a preference relation that was cyclic, right? That had a cycle in it. That's bad. We don't want cycles in our preference relation. So that gives us a sort of a desideratum for what we want to achieve by aggregating. We want to generate a consistent preference relation. We want to generate a preference relation that satisfies the same kind of rationality properties as the individual's preferences ought to satisfy. That is, we want to generate a complete and transitive relation. For the most part, when we're talking about the preference relation here, I'm just going to make the assumption that there are no ties, right? So it's a strict relation, right? That's not necessary. It just kind of makes things easier to talk about. Yeah. Right. Basic idea is you want, at the very least, if you put rational preferences into your aggregation function, that what you get out at the end of it is also a rational preference in the sense of satisfying these sort of consistency properties. Let's not worry about what the aggregation function should do when it's when the individual's preferences are irrational, right? Because you put garbage in, you get garbage out. That's not really where the interesting topic is for us, if you like. So we're going to focus on the idea that we want the aggregation function to be something that takes a collection of rational individual attitudes and outputs a rational attitude, right? That's going to be a sort of basic requirement that runs through all of the kinds of aggregation that we're talking about today. The other thing is that there's no sort of prima facie reason why there's any particular rational attitudes that we shouldn't be able to aggregate, right? The aggregation function should be able to take any rational input, any collection of rational input attitudes, and still be able to generate some kind of rational output. Okay, so so if you think of the process of aggregation as being the action of some function, right? So the function takes the collection of individual attitudes and outputs an aggregate attitude. We want the domain of that function to be unrestricted, to contain all of the possible collections of rational attitudes. Right, so there's two desiderata, right, two properties we want our voting procedure to have, and indeed any kind of aggregation procedure is going, we're going to want it to have something like this, something that tells you, the input can be any collection of rational attitudes, so the domain is unrestricted, and you want to have collective rationality. That is, if you put in rational individual attitudes into the function, you get a rational output. Here's another desirable property, okay? And this is speaking to that idea that we want the aggregation to reflect the attitude of the individuals, right? Basically, if everybody thinks basketball is better than sailing, right? If every individual thinks basketball is better than sailing, then it had better be the case that the output, the collective preference relation, also ranks basketball over sailing. Okay, so here's the idea, right? The astronaut, the clown, and the vampire all prefer basketball to sailing. Therefore, whatever other structure the aggregate relation has, it had better be the case that basketball gets ranked above sailing, right? So this is sometimes called the Pareto condition, after the Italian economist, or unanimity. But sometimes those mean different things. This is one of the tricky things about sort of literature on aggregation, is that there's lots of different formal results that are described in slightly different formal frameworks, and there's only so many words for describing a property, something like this. So sometimes these terms get used interchangeably, and sometimes they mean different things. We'll encounter this again when we talk about systematicity as well. But the basic idea is, it's sort of like, well, we've got to respect the individual's preferences, right? And this is one aspect of respecting the individual's preferences. If they all agree that basketball is better than sailing, that had better be the kind of thing that gets put in. If one option is ranked above another, according to every individual, then it had better be the case that same ranking occurs in the aggregate preference. So Pareto condition, or unanimity, is another thing we want to satisfy. Another aspect of treating individuals fairly is not completely ignoring their opinions. So notice here what's going on is that regardless of what the other two individuals' preferences are, the group preference is just the same as the vampire's preference, right? And the idea is, if that's the case, regardless of what the vampire's preference is, right? So remember, this is a property of the function, so these properties can appeal to these sort of structural features. If the aggregation function always just gives you the group opinion is whatever vampire thinks, then that doesn't seem like a very good aggregation, right? I mean, it satisfies, the input. You can throw in any collection of rational preferences, as long as you've got, and then the function just picks out vampire's preference, right? And if vampire's preference is rational, the input is rational, then the output will be rational. So it sort of satisfies a bunch of the other properties, but it seems kind of unfair, right? It's not fair that regardless of what the other agents think, it's always Vampire's preference that gets reflected in the group preference. So another property that we want our function, our aggregation function, to have is basically not that, right? No individual should be a dictator in the sense of being such that their preference is always perfectly reflected in the group preference, right? And that again is, it's this idea of fairness. It's about responding to the preferences of the individuals, all of the individuals, and not just a dictatorial preference. So unanimity, non-dictatorship, and now we've got the independence of irrelevant alternatives, which basically is another property that we want our voting procedure to have. Basically, the idea is that when determining what the aggregate preference should be for basketball over sailing, right, the relevant information is just how do the individuals rank basketball and sailing, right? The idea is that where golf is in the individual rankings, for example, is irrelevant to the ranking of basketball over boating, over sailing, right? So the idea is if you've got the individuals here, right, with their preferences for the three outcomes, right, if what we're interested in determining is just what ranking to give to basketball and sailing, the only information we're appealing to is how do the individuals rank basketball and sailing, right? So that's the independence of irrelevant alternatives. It's basically saying where other options are in the ranking doesn't make a difference to how basketball and sailing are ranked. Okay? So that's the independence of irrelevant alternatives. Now, Arrow's theorem basically says that those properties are not jointly satisfiable. Right? That's the impossibility. So universal domain, right? Any rational input, collective rationality, rational output, unanimity or Pareto, respecting the case when everyone believes the same thing or has the same attitude, non-dictatorship, and independence of irrelevant alternatives. Something's got to go, right? The way that the proof kind of works is you say, if it satisfies universal domain, collective rationality, Pareto, and independence of irrelevant alternatives, then it's a dictatorship, right? That's how the proof goes. That's how one of the proofs goes, how Arrow's proof went. Right, there's no aggregation function from a collection of complete and transitive relations to complete and transitive relation that, sorry, I'm saying one thing and have written something else. An aggregation function from complete transitive relations to a complete and transitive relation that has a universal domain and respects unanimity and independence of irrelevant alternatives is a dictatorship. There is an individual who's a dictator, whose preference is always reflected in the group preference. Right, so that's the first sort of classic limiting result. Right, we have a collection of desirable properties and we can't have them all. Right, we can't satisfy them all. So something's got to give. Arrow's result was sort of incredibly influential, and lots has been written on it. Lots of modifications of the axioms, lots of analyses of how you might escape the impossibility, right? And you can kind of classify different methods for voting by which of these desirable properties they don't satisfy.
Can I interrupt for a question?
Yeah, sure.
Or we go to the end. Okay, so Alex is asking the downside of a system which does not respect the independence of irrelevant alternatives. What would that be?
Right. Yeah. So so one odd feature of not satisfying the independence of irrelevant alternatives is basically adding things to the menu changes your opinion. So yeah, it's sort of tricky. Yeah, so basically if the aggregate preference doesn't satisfy independence of relevant alternatives, then it kind of matters what options are available. And this, you see, so standard sort of majority voting, you see precisely this kind of pattern, right? In the sense that let's say there's just two candidates, right? The red candidate and the blue candidate, and 60% of people like the red candidate and 40% of people like the blue candidate. So in a vote between the red candidate and the blue candidate, the red candidate wins. Now imagine a case where there's three candidates, right? So there's a blue candidate, and then instead of the red candidate, there's an orange candidate and a pink candidate, right? 30% of people vote for the pink candidate. Oh, sorry, there's a red candidate and a third candidate, say yellow, right? So you've got red, yellow, and blue. Now, some of the people who vote for the red candidate in the two-party system vote for the yellow candidate in this three-party system, right? So even though the red candidate beats the blue candidate if there's no third candidate, the addition of this yellow candidate who doesn't win the election causes the preference, the group preference to switch. And now there's more people who prefer blue. So the blue candidate now wins because the yellow candidate sort of splits the red vote, if you like. So it's that kind of phenomenon of like adding items to the menu, if you like, items that don't win the vote can still affect which of the other candidates wins. Sorry, that was a bit sort of sketchy because I hadn't sort of prepared that. It's a good question, and you can sort of turn that menu dependence, if you like, into a sort of you can, if you know that the group preference is menu dependent in this way, you can manipulate the outcome by manipulating which options are on the menu, right? And that seems like a bad thing. But yeah, so it's in a sense it's a bit more of a sort of a theoretical theoretically desirable property, whereas there are sort of more straightforward, like fairness reasons for thinking that the other properties should hold. And like I said, lots of actual voting procedures, like standard first past the post voting, majority voting, plurality voting, doesn't satisfy independence of irrelevant alternatives. So yeah, people are comfortable with voting rules that don't satisfy it. or at least some people are. But yeah, it's a good question. Okay, so there's our first kind of limiting result. Let's just mention briefly one kind of escape route from the theorem. So independence of irrelevant alternatives is also stronger than it sometimes appears, stronger than it might appear in the following sense. Here's what IIA says again. Preference for basketball over sailing should depend only on how the individuals rank those two options. Right? Now that's doing two things, right? It's restricting how the preference for basketball over sailing is determined. The aggregate preference for basketball over sailing is determined only by those two options, basketball and sailing, and what the individuals think about those two options, right? But also in the way it's framed here, and also in the sort of formal cashing out of this, the property of independence of irrelevant alternatives also requires that the preference for basketball over sailing only depends on how individuals rank order those options, right? So independent of irrelevant alternatives actually sort of says a lot more than you might think, in the sense that it basically rules out accommodating any idea of the strength of preference, right? Let me just go back and show you an example of this. So here we are, independence of irrelevant alternatives. What it says is that these are the only things that matter, right? How the individuals rank order basketball and sailing, right? Now, but imagine that we're in the following sort of situation. The astronaut and the clown both prefer basketball to sailing, but they're fairly happy with both, right? They're both pretty good, but they slightly prefer basketball to sailing. Whereas the vampire really hates basketball and really loves sailing, right? So that strength of preference just can't have a role if the voting rule satisfies independence of relevant alternatives, right? And it might be like if you want to, accommodate that kind of strength of preference, that seems like something you might want to accommodate in a voting rule or in some kind of aggregation methods. So that's just to sort of sketch one avenue, is then exploring how you might reasonably elicit strength of preference in a fair way, and that's it's a whole topic we won't really have time to touch on here, but that's another way, in fact, that the independence of relevant alternatives is actually kind of too strong, and maybe the downsides to not satisfying it are acceptable. Although those in fact independence of relevant alternatives kind of builds in two quite distinct properties almost, in a way, right? There's the menu independence property, which is kind of plausible, I think, and then there's this you're only allowed to account for the ordinal information property, and that's less plausible, right? I should crack on with the next couple of sections if we want to finish on time. So judgment aggregations. We're moving now on to a different kind of attitude. We're not going to talk about preferences anymore. We're going to talk about propositional knowledge. So you've got some language of, some logical language of propositions, and then basically individuals that have, binary beliefs, yes, no, about those propositions. So they believe some propositions to be true and they believe others to be false. Now, here's an example of a collection of propositions that you and you might want to aggregate different individuals' attitudes about these propositions. So this comes from the literature on sort of jurisprudence, in fact, and was picked up by some logicians and philosophers more recently. So proposition P, right? The defendant was negligent, right? That's one proposition. Second proposition, if P then Q, right? If the defendant was negligent, then he is guilty of a crime, right? And then the consequent of that conditional, the defendant is guilty of a crime, okay? Those are the three propositions that we're considering having attitudes towards. Now let's imagine that this is these are the propositions, the facts of which, you know, need to be addressed or decided by a jury of 3 judges, right? So the astronaut, clown, and vampire, they had their nice afternoon off. Next morning, it's back to work as judges in a court. And each of those individuals has attitudes to each of those 3 propositions. They either think they're false or they think they're true, right? So astronaut thinks all 3 propositions are true. Clown thinks that the first one is true, P is true, and then the other 2 are false, right? And the vampire thinks that only the conditional is true and P and Q are both false. So each individual has rational, that is consistent, you know, logically consistent beliefs, okay? But if you just take like proposition-wise majority voting, right, the majority collection of opinions is inconsistent, right? Because 2 of the 3 judges think P is true, right? So P gets true in the majority. 2 of the 3 judges think if P then Q is true, so the majority thinks if P then Q is true, and 2 of the judges think Q is false, right? Now that's inconsistent. If you think P is true, and if you think if P then Q is true, then you have to think Q is true, right? So it's just logically inconsistent to think that Q is false there. So that's a problem. And you can kind of see there's something of the same kind of, you know, Condorcet cycle type kind of issue going on here, but we won't explore that analogy too closely. But basically, here's, you know, there seems to be some kind of problem here. This proposition-wise majority voting, it doesn't yield consistent outputs. Okay, so that isn't going to be a good way to aggregate propositions. So basically, we're building up towards an impossibility theorem in the same way we did before, right? And some of the conditions are pretty similar, right? Again, we want the aggregation function, right, which is now going to take sets of, you know, a profile of propositional attitudes, right? True or false for each of a collection of propositions for each agent, rather than preference relations over the options. And it's going to aggregate a collection of you know, true or false judgments about the propositions in the agenda. We want that function to have a universal domain again, right? We also want to have a kind of collective rationality, right? In the sense that we want the output of the voting procedure to be consistent, logically consistent. So remember, collective rationality in the case of Arrow's theorem meant complete and transitive relation as the output of the aggregation procedure. Here, same kind of idea, collective rationality, what that means in the context of aggregating propositional knowledge is we want a consistent and complete set of judgments. So true or false for each of the propositions in the agenda. Now we have some slightly different sorts of properties that still have the flavor of the some of the properties we had for voting. So we want the aggregation procedure to be systematic in a certain way, in a way that kind of has echoes of independence of irrelevant alternatives, right? In the sense that the aggregate, so the value, the truth value, true or false, that's assigned to some proposition P should depend only on the pattern of individual judgments about that proposition. And you can see that's got something of the same kind of flavor of independence of relevant alternatives, right? It's only, you know, the aggregate attitude about this thing depends only on the individual attitudes about that thing. It's the same kind of idea. And we want another property that has echoes of in the non-dictatorship property from voting, right? That we might call anonymity. So this is sort of strictly strong, logically stronger than non-dictatorship, right? Which is basically that the aggregation, the output of the aggregation should not depend on the order of the individuals, right? So the idea is you have a collection of individuals, collection of the attitudes of individuals, the output for that, the aggregate for that collection of individuals should be the same as permuting the individuals, swapping the individuals around, and then aggregating that permuted collection of individuals. That should be the same as the unpermuted thing. And that's capturing the sort of property of anonymity in the sense that it doesn't matter who, you know, the location in the list of individuals, right? It doesn't matter which individual you are, every individual's vote counts the same. You can see that's logically stronger than dictatorship, right? Anonymity rules out a dictatorship because if it has to be invariant under these permutations, you can't kind of pick out the dictator through all the permutations. And, you know, unsurprisingly, if you like, these properties are jointly inconsistent. So universal domain, collective rationality, systematicity, and anonymity, not jointly satisfiable. For a sufficiently rich agenda of propositions. So I didn't really talk about that, but the agenda is just the collection of propositions we're talking about. So for the example we started with, right, the agenda is these three propositions: P, if P then Q, and Q. And the important thing to notice about this collection of propositions is that they're logically related to each other, right? So there's a sort of logical richness, if you like, to the collection of propositions that we're aggregating the attitudes about. So there's a condition of having a sufficiently rich agenda of propositions. If you just had, you know, just A and B and no logical relations between A and B, then it's possible to aggregate in a consistent way, because consistency is easy if there's no logical relations between the propositions. Any collection of truth values for them is permissible, basically. So it's only when you start having logically related collections of propositions that you get impossibility results. And there's a lot of work on different sorts of strength of richness condition and the other conditions in the theorem, and lots of theorems that sort of say, you know, if your agenda is this rich and your your aggregation function satisfies these and these properties, then impossibility. But if you make the agenda weaker, but you make the properties that the aggregation function has to satisfy stronger, you also get an impossibility result. So there's a lot of there's a few moving parts there and a lot of work on exploring that kind of topic of agenda richness. in the case of propositional knowledge bases. But I didn't really want to sort of get into that because it's a bit sort of tangential given where we want to go with talking about the positive results for imprecise probabilities. So one thing to note here is that we didn't really talk about any kind of unanimity preservation property in this particular theorem that I'm sketching here, but unanimity preservation or something like it does play a role in some of these theorems about proposition aggregating propositional knowledge. Good. So that's voting and judgment aggregation done, and now we're going to talk about probabilistic aggregation. So here I'll say at the top that this is maybe a little bit more contrived in the sense that I wanted to frame probabilistic aggregation also as being subject to a kind of limiting result, an impossibility result, in the same way that the other two are. That's not typically how it's framed in the literature, and we'll get to that in a second. Right. Now we're talking about the case of agents whose attitudes are probability functions. So each individual has a precise, additive probability function, and you want to aggregate that into a group probability function. So one method you might use for doing that is just linear averaging, right? Linear pooling, right? So the output is just the weighted average of the inputs. Okay, that's a probability function, right? That's if the weights add up to 1, right? Or are non-negative and add up to 1, obviously. That's going to be a probability function, and it's going to be a sensible kind of aggregate. Now, what sort of problem does this aggregate have? Well, one property that this linear pooling doesn't satisfy, I mean, this is well known, I imagine a lot of people already know this, is that linear pooling doesn't preserve independence, right? Here's a sort of simple numerical example, right? So P1, for probability function P1, X and Y are independent of each other, right? Probabilistically independent, and X and Y both have probability a third, according to P1. For P2, X and Y are probabilistically independent of each other, and they each have probability 2/3. Okay. Now let's think about the unweighted, the equal weighted aggregate of these two, linear pool of these two. Call it Q, right? Simple calculations. I think I've done these calculations right, but I may be wrong. I'm pretty sure I got them right. For this aggregate probability, right, the joint of X and Y is not the same as the product, right, of X and the probability of X and the probability of Y, which means that they are not independent. Okay. So linear pooling doesn't preserve independence in the sense that X and Y were independent for P1 and for P2, but not for the pooled probability Q. That means that linear pooling doesn't satisfy another desirable property, which is basically commuting with update, with conditionalization. What I mean by that is the desirable property is the following. You should get the same result if you conditionalize each member each individual's probability on the same thing, and then aggregate the conditionalized probabilities, that should be the same result as aggregating the priors and then conditionalizing the aggregate, right? So that you should, those two properties should, those two procedures should commute. If linear pooling doesn't preserve independence, it's not going to commute with conditionalization in that way. So there's two problems that linear pooling has. Okay. So we can kind of turn this into a kind of impossibility theorem, if you like, although this isn't typically what people do. So we have a kind of universal domain, right? Any collection of probabilities should be a permissible input, collective rationality. The output should be a probability function. We want the aggregation procedure to preserve unanimity, right? In the following sense, if everybody has probability 1 for x, then the group probability should be 1 for x. It's quite a weak property in a sense, because it's only preserving unanimity about probability 1 events. And if we also want to preserve consensus about independence, right, in the sense that if x and y are probabilistically independent according to every member of the committee, if you like, then the output should also satisfy the same independence. And we want our probability function to be systematic. What do we mean, by systematicity in this context? Again, it's the same kind of idea, right? The aggregate probability for some proposition x depends only on the collection of values assigned to x by the individual probability functions. Okay, so those properties are incompatible. Okay. Why is that? Essentially, that systematicity property plus preserving unanimity about probability 1 events characterize linear pooling, right? If your aggregation procedure satisfies systematicity and unanimity preservation and universal domain and collective rationality, then linear pooling. And in fact, a weaker sort of unanimity preservation, together with a requirement about commuting with conditionalization, commuting with update, entails that you have a different kind of pooling procedure, geometric pooling. Right. So that's the impossibility result for probabilistic pooling. Now, the reason I said that that's a little bit contrived is because typically in the probabilistic pooling literature, people aren't talking in terms of an impossibility result, they're talking in terms of characterization results. So this collection of properties is sufficient for your aggregation procedure to have this functional form, linear pooling, geometric pooling, or whatever. But you can turn that into an impossibility by saying we also want the aggregation to satisfy this further property, right, preserving probabilistic independence, which is incompatible with linear pooling, for example. And in fact, you can see other impossibility theorems as examples of characterization sorts of results, right? Like the Arrow's theorem, remember I said the result basically is if you satisfy all of these properties, then it's a dictatorship, right? So in a sense, you could read that as a characterization, right? If you satisfy these properties, then it has this simple functional form, right? It's a dictatorship. So there's not like a deep sort of difference in kind between results that you sort of see as impossibility and results that you see as a characterization. Okay, so I sort of rushed through the probability stuff a little bit there, but you get the idea. It's the same kind of picture. Okay, because I want to spend the last 20 minutes or so, I'll probably try and go for, just to give you a sketch of the way these results tend to be proved. I'm going to do this in a very kind of abstract way that hopefully applies to all of the different impossibility results we've seen. I'm beginning to question the wisdom of doing things this way rather than just giving you an example, but we'll see. Okay, so we've got a collection of agents, a collection of individuals, n. We'll just number them, 1, 2, 3 up to n. Okay, little n. And then we've got z, which is going to represent the possible opinions that agents can have. Now we're going to say that this collection of possible attitudes is a lattice. Okay, basically it's a partially ordered set. Okay, so if you've got two possible opinions, right, x and y, possible opinions in z, we read y is less than x, right? We're going to read that as x is more informative than y, right? Or x accepts y, right? So if we think of the set of, if we think of opinions as the easiest one to do, as for propositional knowledge, for example, this, if you like, so if you have an agent's opinion is basically a set of propositions they believe, right? It's the set of propositions they think are true. This is going to be, this relation is going to be basically the subset relation, right? So y is a subset of x. X is more informative than y in the sense that there's more, x believes more, or the agent believes more things in x if it's a bigger set, right? So the top element of this partially ordered set of possible opinions is the inconsistent opinion. Now that makes sense if you think about an opinion, if you think about the case of the set of possible opinions where the agent who believes all the possible propositions, right? That's inconsistent. It's inconsistent to just fully believe all of the propositions. So that's why the top element is the inconsistent opinion. The elements of this lattice of possible opinions that are just below the top element are basically the maximally informative consistent opinions, right? So just below the collection of all opinions is the maximally, so the biggest sets of propositions you can have that are consistent, that are not like equivalent to the top element. Yeah, sorry. So if we're thinking of the collections of opinions as the logically closed sets of sentences, right? So we'll come back to this idea of this sort of lattice of opinions in the second part. So I'm sort of glossing over this fairly quickly here, but we'll talk about this again in the second half of the second part of the session. So propositional knowledge bases, satisfy this sort of lattice structure. where, well, I've said there where the dual of where the relation is the dual of the entailment relation. So that's if you think of a propositional knowledge base as represented by the logically strongest sentence entailed by a set of sentences. If you think of a relation as just a set of ordered pairs, right? So a preference relation. So if you think about sort of the collection of all sets of ordered pairs on some set, that's a lattice ordered by the subset relation, and the preference relation, the complete and transitive relations, are a sub-lattice of that. Okay. I'm going to skip that for now. This is quite a lot to sort of throw at you at the end here. I'm sorry, but I want to give you just enough of the flavor of the result that you can sort of see where it's going. Right. So this pi here is going to essentially represent the profile, the collection of opinions of the individuals, right? And the way we're going to do that is pi is just going to be a function. You give pi an individual, the number that corresponds to an individual, and it gives you the opinion that individual has, right? So call pi the profile, right? The collection of individuals' attitudes. Call pi rational if essentially every individual's attitude, right, the output of pi for every I is not inconsistent, right? So big pi there is then the set of rational profiles, and that's what we're interested in, right? The collection of rational profiles. Bit of sort of housekeeping terminology. Pi of a subset equals Z, subset of the individuals, if every individual in A has opinion Z, okay? Right, so the aggregation function is going to be a function from the functions from N to Z, right, the profiles, although in fact we're only going to be interested in the case of the rational profiles, pi, big pi, but we'll just define the function from the full set Z to the N to Z. So Z again is the collection of attitudes, right? We'll call it an aggregation function. We'll call it F, we'll call the aggregation function rational if it gives a consistent output, a inconsistent output for every rational input. Okay. So for the purposes of making the proof sketch slightly easier, we're just going to talk about complete aggregation functions. What I mean by that is essentially the output of F is always maximal in the order, right? So maximal consistent opinion. We can weaken that a little bit if we like. Right, so last bit of formalism, I think. Essentially Z, so pi here is the collection of individuals who accept Z according to profile pi. Okay. So you have a collection of individuals who have the collection of attitudes characterized by pi. Z, so pi here is the subset of that collection of individuals who accept Z, i.e. by having their opinion entail Z or be more informative than Z. And then Z with a line through it is the collection of individuals whose attitude is inconsistent with Z. Okay. So last bit of terminology now, right? We want we want to talk about a collection, a subset of the collection of individuals, it being decisive for an aggregation function with respect to some opinion Z, some element of the lattice of opinion Z. What we mean by that is basically the subset M is decisive if every individual in M accepts Z and every individual outside of M has an opinion that's inconsistent with Z, right? If those two properties hold, then the aggregation accepts Z, right? So that's what it is to be decisive. Basically, the individuals, if the individuals in M all believe Z and all of the individuals outside of M have, believe not Z essentially, then the aggregate still believes Z, the output of the aggregation believes Z. So in a sense, like the subset M can kind of force through their belief in Z, right? That's the idea. So that's what it is for a subset of the individuals to be decisive for the aggregation function F with respect to a certain opinion Z. Right. Obviously, N, the whole set, is decisive if F is satisfied as unanimity preservation. All right, cool. Omega of Z, basically, it's all of the decisive sets for Z, right? If we fix F, right? All of the collections of individuals who can force through their belief in Z. Okay. So here are the properties we want the aggregation function to have. Basically, neutrality is a kind of systematicity, right? It's saying if a collection of individuals, if the collection of individuals that accept A according to profile pi is the same as the collection of individuals that accept B according to profile pi prime, then A should be treated the same way when you aggregate pi as B should be treated when you aggregate pi prime. Okay, it's the same kind of systematicity type property. And then we've got a kind of unanimity preservation sort of thing. Basically, if more individuals believe A or accept A according to pi prime than do according to pi, the profile, then if A is accepted when fewer individuals believe it, accept it, more, it also has to be accepted when more individuals accept it, right? So that's the idea. So if you've got a collection of 10 people and 7 of them believe some proposition and the aggregate outputs that proposition is believed, then if some people change their mind and so now 9 people believe that proposition, it had better still be the case that proposition is believed by the aggregate, right? It shouldn't be that you have people change their mind to come to believe a proposition and that causes the aggregate to no longer believe that proposition. Right? That's the idea of monotonicity. It's a sort of stronger version of Pareto. It's not quite strictly stronger than Pareto, but it's this plus another property entail Pareto, but we don't need to get into that. I've described these axioms as, so this is just for people who sort of are interested in that or familiar with the lattice theory stuff. These axioms are for atomistic lattices, but that's not necessary. There are versions of these axioms that don't rely on the lattice being atomistic. Right. So here's, and this is going to be very sort of big picture sketchy, but basically if F is rational in the sense that rational inputs give you a rational output, and complete in the sense that it always gives you a maximal consistent opinion as output, and it satisfies neutrality and monotonicity, which are a kind of systematicity and a kind of consensus preservation, and the lattice Z is sufficiently rich, the lattice of opinions, the collection of all opinions is sufficiently rich, then the following things hold. The collection of decisive subsets for X and for Y are the same. So the same individuals can force X as can force Y for any X and Y, right? Which is kind of surprising. If some collection of individuals, some coalition, right? Some collection of individuals, a coalition is decisive, can force any proposition they all agree on, and B is a bigger coalition, right? Then B is also decisive, right? You can see how that sort of follows from monotonicity, really. If A is decisive, if a collection of individuals A is decisive, then its complement, so the collection of individuals not in A, is not decisive. Okay. And finally, if A and B are both decisive coalitions, then their intersection is also a decisive coalition. Okay. So if you can prove those four things, right, you're done. Why? Because these four properties mean that the collection of subsets of individuals, that are the decisive subsets of individuals, is an ultrafilter. So satisfying the first three of those means it's a filter. Satisfying the third one, the fourth one means it's an ultrafilter. And what that means is that since the number of individuals is finite, omega is a principal ultrafilter, because all ultrafilters on a finite set will be principal. And so there's some individual I, the principal element for that ultrafilter, and that I is a dictator, because it's a single individual that's decisive, that can force any opinion that it has, right? So that's the basic idea. A lot of the proofs have that kind of structure. Essentially, you show that you exploit this idea of the decisive coalition, and effectively what you're doing is you're showing that the collection of decisive subsets is an ultrafilter, and A is finite. Now, there's lots of ways, particularly for Arrow's theorem, so the first that first sort of classic result. There's lots of different ways of proving it. The book, the primer on social choice theory that is in the syllabus I sent Marco, has, I think, 3 or 4 different proofs in it that all seem kind of radically different. It's kind of interesting. But this proof sketch is the same kind of structure that you see in the case of the propositional knowledge, and it's also kind of similar to results that also apply to the probabilistic case. It's the same kind of approach. just for people who are sort of interested in abstract algebra stuff, if you let Z be, instead of a lattice, you make it an NV algebra, which basically has a complement, and it's essentially the sort of, yeah, no, it doesn't matter. If you know what an NV algebra is, you can do the same kind of result with NV algebras. Essentially, you show that aggregation has to be an NV homomorphism, and the only NV homomorphism into the NV algebra, essentially the sort of the real line, is a linear pooling. It's just for the aficionados. Another useful sort of, and another interesting connection between the different so propositional knowledge, probabilistic knowledge, and so on. You can think of propositional knowledge, right? So yes, no beliefs, true, false beliefs about a collection of propositions, as essentially a degenerate probability, right? A probability that just assigns zeros and ones to all of the propositions. Now, if you think about what linear pooling would be for a degenerate probability function, right? It's going to be dictatorial. Essentially, the weights are going to have to be 1 and then 0 for all of the others. Because if there's any disagreement among the individuals, any non-degenerate weights are going to give you a value other than 0 and 1 as the output. Okay, so sorry that the last sort of few minutes there may have gone by a little quick, and if you're not familiar with some of that stuff, that may have been too much at once. But I hope to have given you a kind of flavor of different kinds of aggregation theorems, impossibility theorems for different kinds of aggregation. What we're going to do in the next session after the break is we're going to look at the positive story. So we're going to focus on imprecise probabilities, and we're going to say, what can we do? What kinds of methods for aggregation can we generate for imprecise probabilities? And what sort of properties can they satisfy? And brackets, how do we avoid these kinds of impossibility results when applied to imprecise probabilities? Okay, thanks, and I'll see you in a little while. It satisfies some of the properties and not others, right? It's as you'd expect. I mean, yeah, it's going to be within the convex hull of the union, obviously. It's not going to, yeah, because it's sort of similar to linear pooling. It's going to satisfy more or less the same properties linear pooling does. Maybe that's where I skipped it. Okay, so what that coherent approximation approach did was it took a set of imprecise probabilities and it output a precise probability. There's actually a method that does the opposite, right? You can take a collection of precise probabilities and output an imprecise probabilities, right? You can see how it's going to work. You take the convex hull of the union. Right? So this, sorry, these slides are out of order. I don't know what's happening here. So the convex hull of the union can take a set of precise probabilities and output an imprecise outcome that overcomes some of the problems we had with precise aggregation methods, right? Remember, there was a tension in the precise probabilistic aggregation case between systematicity, right, which was the aggregation has to be only depend on the values assigned to, so that the aggregate probability for X depends only on the input probabilities for X. So that kind of systematicity, which is what McConway calls setwise function property, and I can't remember whether what I said just then was the weak or the strong version, but anyway, so that kind of systematicity was incompatible with commuting with conditionalization in the presence of some other conditions, because this, if your aggregation procedure is suitably systematic, it's linear pooling, and linear pooling doesn't commute with conditionalization. But this sort of convex IP pooling, right, basically you just take the convex hull of your set of precise inputs, and you have that as your output. That does commute with conditionalization. And indeed, the same is true if you let the inputs be imprecise as well. So that should have been along with the other slides about convex hull of the union. Okay, so we've talked about several different methods for imprecise aggregation. The convex hull of the union, right, which is going to be very big, may be useful for some purposes. We talked about linear pooling, which is sort of simple, but doesn't satisfy some of Wally's desirable properties. We talked about the coherent approximation principle, which yields precise output, which may be useful in some circumstances, but is computationally intractable for all but the smallest. Well, no, I mean it's not. It's doable for small groups, but it is a non-trivial optimization problem that you're doing. Okay, so what I want to do in the last, how are we doing for time? Yeah, okay, so I may have to breeze through this a little quickly, sorry. What I want to do is basically talk you through some of my recent work on this. Basically, we're going to get to the stage where we can say, look, all of these, or versions of all of these methods for aggregating imprecise probabilities are instances of this particular framework, which is nice. Okay, so we talked about propositional knowledge bases, right? We talked about having agents whose opinions are sets of sentences that they think are true, right? You can represent an agent with a propositional knowledge base by the set of sentences they think are true. Those sets of sentences are ordered by the subset relation, partially ordered by the subset relation. Though that, subset structure has essentially this lattice structure. There's a least upper bound and a greatest lower bound, which are essentially intersection and union of sets of sentences. There's a coherent substructure in the sense that some collections of sentences are closed under logical consequence and consistent, right? That's a property that's preserved by intersections. And the top of that lattice of sets of sentences is the incoherent sentence. It's the set of all sentences, which is incoherent. Okay. Now, some facts about lower provisions. Essentially, the same properties are true of lower provisions. They're partially ordered by dominance, pointwise dominance. They have the lattice structure. You can do least upper bounds and greatest lower bounds on lower provisions. There's a coherent substructure. There are coherent lower provisions. That property is preserved by pointwise minima, right? And the top, right, the thing that dominates all lower provisions is incoherent. It's the thing that assigns, infinity to all gambles or whatever. So abstract away that structure, and you can see now that this is kind of similar to the lattice structure we were talking about when we gave the proof of the impossibility theorem, or the sketch proof of the impossibility theorem. We had the same kind of lattice of opinions type structure. Right, so we've got a set of belief models ordered by this informativeness relation. There's a coherent subset of that, right, which is closed under infima. The top of this lattice is not coherent. We call this a belief structure. That the members, the elements of S are belief models, the elements of C are coherent belief models. Okay. So M is the set of coherent models that are maximal according to this ordering. So these are the things that are just above, or just below the top element, right? So if you're thinking about sets of sentences, these are the maximal coherent sets of sentences. If you're thinking about lower provisions, these are the linear provisions, right? Lots of things satisfy this belief structure. So this, sorry, I should have said this is not original to me. This work was Kurt Coman in 2005, a really great paper called Belief Models and Order Theoretic something, an order theoretic exploration. I can't remember what the last word of the title is, but anyway, my contribution is later on. But he points out, look, lots of things satisfy this propositional knowledge bases, lower provisions. You can add a bunch of other examples of things like that, ranking functions, certain kinds of modal logic that have a well-behaved consequence operator, sets of desirable gambles, choice functions, preference relations, comparative probability relations, comparative confidence relations. These are all satisfy this belief structure framework, or are very close to satisfying it, so that we can sort of do some fiddling to make it fit, or versions of these satisfy the belief structure framework. Why am I talking about this belief model stuff? Well, basically because this is now bringing a couple of things together that we've mentioned briefly already. So because one example of the belief models framework is the sort of propositional logic stuff, we can essentially exploit all of those results in propositional logic and computer science and so on. So there's a lot of stuff about belief merging, right? The merging of databases and kind of abstract stuff inspired by that kind of idea that assumes that we're talking about propositional logic, right? So you get some axioms for what you want your aggregation procedure to look like, and you get some results, right? Lots of different kinds of characterization results. And essentially, because this propositional logic is an instance of the belief model stuff, we can basically just lift all the results into the abstract framework and then apply it, to the other examples of belief models, for example, lower provisions. So, for example, we can, lift the axioms up, right? We lift the result up. That's a fairly straightforward kind of translation from the propositional logic language into the belief models framework. It's normally fairly straightforward to do that sort of thing. And then the proof, we can sort of piggyback on the proofs for the propositional logic case. So that's the basic kind of idea. And de Kerman's paper, he does this for not for aggregation, but for belief revision, right? So he does sort of AGM style belief revision for belief models. And what I did in my ISIPT paper from a couple of years ago was do the same thing for a particular class of aggregation procedures. So basically, I mean, I'm repeating myself in some of these slides because I sort of copied these over from other presentations I've given and didn't have time to really edit them for this audience. But basically, look, we're doing the same thing we were doing before, right? We've got a collection of individuals, a collection of belief models, and one kind of assumption we make up right off the bat is that this collection is a multiset, right? Which basically kind of builds in the anonymity, the permutation invariance, because you just get the set. You don't get any kind of order information about the individuals. It's a multi-set, so you can allow two individuals to have the same attitudes. And you want a function that takes that multi-set and outputs a belief model. Multi-set of belief models, outputs a belief model. We want it to respond to the opinions of the agents, right? We want it to be as close as possible to the opinions of the agents, and it must treat the individuals fairly, whatever fairly means, right? But not being a dictatorship, for example. And it must satisfy some independent constraints. So we haven't really talked about independent constraints here, but basically you can kind of say, I want to aggregate these and these beliefs, and also I want the aggregate to say that this is true, right? This particular proposition is true or whatever. So you can just add in those kinds of independent constraints. For example, if you're merging different databases and there are particular bits of information that you want to be put a certain way in the output, you can plug those in to this sort of framework. So we then essentially develop a collection of axioms for the merging operator, this delta, which satisfies a lot of Wally's conditions, not all of them. Doesn't satisfy the mixture closeness one, for example, or reconciliation, but it satisfies most of the others. It satisfies all of the others, I think. And then we can use the existing literature about merging operators in propositional logic to generate results in the belief models framework, which can then be applied to, say, the imprecise probability framework. Right, I'm just going to skip that first point. So one method we have for that, one sort of way people do merging is essentially something like the kind of, that we saw in this coherent approximation principle idea. We develop some notion of distance, right, over M, so over the maximal coherent belief models, the maximal consistent sets of sentences or the linear provisions or whatever. And then you just need a method for aggregating distances. So you kind of reduce the problem from aggregating these belief models, whatever they are, to you just have to aggregate a bunch of distances and then minimize that distance, minimize that aggregate distance. We haven't really talked about AGM, so I'll skip that. But if you're interested in AGM, there's a very, very close connection between them. So the kind of results that you get in the propositional logic literature, and that I just basically piggybacked on and lifted into this belief models framework, are things like the following. So every merging operator that satisfies these properties, I've listed the properties at the end, and we can have a look at them. So every merging operator that satisfies some collection of properties, well, we won't talk about the relation. So, sorry, I'm just skipping this stuff about entrenchment relations for time. so every distance between maximal belief models and method of aggregating distances that satisfies a bunch of properties yields a merging operator that satisfies these properties, including most of the ones that Wally was talking about in the context of IP. So that's really useful in the sense that we now have a way of kind of generating methods for aggregating, right? We're not sort of just stumbling around blindly. We can just say, okay, well, all we need to do is think up some method of measuring distances between the maximal coherent elements of our belief model. And then this theorem tells us that that's going to yield a merging operator that satisfies a bunch of desirable properties, right? So that's a sort of really useful way of sort of reducing the problem to just finding some kind of measure of distance between the maximal coherent elements. Now, remember, if we're thinking about imprecise probabilities, the maximal coherent elements in the belief model are essentially the linear provisions, essentially the probability functions, right? Being a bit sloppy, glossing over the distinction there, right? And we've got a bunch of methods for measuring distance between probability functions. There's a ton of them, right? So all that work's already been done. So this gives us a nice way of generating interest or in generating new aggregation procedures. And here's the sort of upshot why I've talked you through this stuff in this context. The upshot is that basically a version of the convex hull of the union aggregation procedure, a version of this sort of coherent approximation type approach, it's not quite the same, it's similar though, and a version of this sort of maximal coherent subset aggregation procedure. They're all special cases. They're all instances of this kind of merging of belief models when applied to imprecise probabilities. The difference being just what method of distance you use. Yeah, I think you just change the method of distance. I think the aggregation method of aggregating distances is just summing in each case. So that kind of shows you, straight away that these different methods for aggregating imprecise probabilities satisfy a bunch of properties. Now, it may have been tricky to prove directly that these properties are satisfied by each of these methods for aggregating distances, but you sort of get it for free once you can construct them using this sort of machinery. So this is, this is the kind of formal work I do. It's very lazy. I find neat results other people have done and then kind of use them to crank the handle on interesting results. Okay, so I will. I'm basically nearly done. I have some bonus material about the details of the belief models, the axioms for the merging operator, and for the distance-based merging. But I'll only really sort of talk through them if there are specific questions, because they're kind of a mess, right? So I'll stop there. I'll say thank you for your attention, and thank you to Marco for organizing this. And I'm happy to take some questions.
Thanks, Seamus. Thank you very much. Yes, I think so. Let's hear if there are questions, and if not, we can carry on and see more in the details. I don't see any question in the chat, so
I can ask a short one there, Marco.
Yeah, go ahead.
Hi, Seamus. So first of all, thank you so much for your insightful discussion. I really enjoyed it. I just have one short question about the distance-based merging. So the formula that you show was, I think, a very general distance-based matrix. So basically, this technique, like there's no specific distance matrix you're using, right? We can use like anything like the Bhattacharya or the Euclidean distance. Anything is pretty a general like distance framework. If that's my understanding.
Yeah.
Right. Let's go.
Yeah, I mean, in fact, the conditions are surprisingly weak, right? So the distance basically has to be symmetric and 0 only when it's a distance between. So it has to give non-zero values to any distinct belief models.
Yeah.
Right. That those are, you know, it's not even really it's not even a metric, right? It's that's the only thing you need to be satisfied. And then the properties for aggregation are sort of more complicated, but basically summing of distances and a couple of other kind of like things that give you like lexicographic orderings satisfy them. But it's basically just, you know, invariance under permutation, kind of monotonicity. There's a few things like that. But yeah, like if you want to sort of sum distances, if you just take the aggregating out of it and just do summing, loads of things satisfy that. These are the only properties you need to get an aggregation procedure that satisfies a bunch of nice properties. I mean, in practice, what happens is that a lot of different methods, a lot of different distances end up giving you the same aggregation procedure or very similar aggregation procedures. So there isn't as much richness to the aggregation procedures you can get out of this as you might think from the fact that the conditions on aggregation are quite weak.
Right.
Because really what the only essentially distances that are, oh god, I'm not entirely sure this is exactly right, but essentially it's something like if your distance is just is an affine transformation of another distance, they'll give you the same aggregation procedure. I'm not sure that's 100% right, but that's basically the idea, that it's really that you're only really appealing to a certain amount of the kind of ordering, the ordinal information of how the distance orders distances between the maximal coherent models.
Right. So earlier you were talking about affine transformation. So I was thinking about the so this affine invariance is assumed to also hold under like for this framework, right? The affine invariance is one of the framework that's assumed in this work over here. Is that a safe assumption?
Sorry, could you say that again?
The affine invariance, because earlier we were talking about affine transformations of the distance. So is it safe to say that for this work that we just looked into, there's affine invariance that's being accounted for in the assumption?
It's not something you put in. It's not an axiom or anything.
Right.
But just because basically the way you use the distance in constructing the aggregation function, right? The aggregation function for the belief models, not the aggregation function for the numbers.
Yeah.
The way you construct delta,
yeah,
the aggregation function using d, the distance, you're only really using some of the information, the kind of ordering information that's contained in d.
Right.
So yeah, it's not an axiom that you put in any kind of invariance under affine transformations, but I'm not entirely. I wouldn't want to say that that's precisely what is happening here, but it's something like that.
Right. Okay. No problem. Yeah, so I actually have another part to follow up to this question. So because I've also dealt with a little bit of distance matrix as well, I'm not sure if it's relevant for this framework that we just discussed, but when you're dealing with, let's say, a distance, like let's say when you have two histograms and all that, and you want to compute the distance based on the number of bins, because you need to have the bins will affect the computation of distance. Is there like any specific criteria in your knowledge, to specify the number of bins in the competition for such distances?
No, I don't know. I mean, yeah, it's sort of, I've not really dealt with any kind of measuring distances between histograms, but I mean, I'd have to think about it some more, but yeah, no, I can't think of anything useful to say to that off the top of my head. Sorry.
No worries, no worries. But nonetheless, thank you so much for your insights and answers to some of the questions that we had. So I'll leave the time to other users. Thank you so much once again for your presentation this evening.
Thank you.
Dominic is asking if you have a simple and useful example for the distance.
I mean, so the Euclidean distance is an example of a distance you could use here, right? Oh yeah, sorry, I'm not sure I've understood the question.
I think it was just, I guess it was just wondering if there is an example that you can think of, like a simple example on top of your head that where what this distance, how would you apply this distance to an example? I mean, I would think like the Euclidean would have an additional property. So this distance is, as you said, is not a metric. So it is a weaker type of, or if you want, I mean, it is something between a distance and a metric.
Yeah, I mean, so to get, for example, the how does that work? Yeah, so the distance, so to get something like the maximal coherent subset aggregation procedure out of this, what does the distance look like for that? Well, you basically, the distance between two belief models is, I can't remember the details, but you basically just kind of, you add up how many members of your set of belief models that belief model is consistent with. Is that right? Sorry, I'm trying to remember this now. I don't have my notes with me because they're all in the other room.
Is it like when you have I mean, there is a way you can visualize a Cradle set, right? So it's, I mean, it's a convex set with vertices, And you mentioned that you have basically, I mean, if you can find the precise probability inside that set that minimizes all the distances, that is something that you can visualize. And it is like, seems quite intuitive, although maybe computationally expensive. I mean, if you think of, if there's a point that has that minimizes all the distances from the vertices, is that something that translates to this more abstract notion or concept, if you want, concept of distance that
yeah, well, so you can sometimes you can visualize it in that way, but the method for say just the maximal coherent subset approach to taking the intersection is sort of harder to visualize like that, because you're not really measuring sort of distances in that sense, but you're measuring how you're measuring how many members that belief model is in. So when you're talking about distances in the sense of distances that you can give some kind of geometrical interpretation to, like the Euclidean distance or the absolute distance, whatever it's called, absolute difference is what do I mean? Anyway, if you've got a metric or something like a metric that has some sort of geometrical interpretation, you can definitely visualize it in the way you're suggesting. For some of the distances in this sense that aren't really much like a metric, it's harder to visualize them in that way. I'm struggling to think of an example, but yeah, I mean, I think the distance, whatever the distance would be for something like, take the convex hull of the union, is not going to be visualizable in the same way.
Ignacio saying if is the idea similar to the Shapley value, just the weighted average of the extreme points? Is that something that?
I don't think that's something I've looked at. I mean, it's an interesting suggestion, but I mean that isn't one I've explored. Yeah, but I should maybe. Thanks.
And this Kevin saying, can you just take the maximal pairwise Euclidean distance that satisfies symmetry and distance is 0 only when identical? So is it like maximal pairwise Euclidean distance? Yeah.
Yeah, so the distance between two creedal sets is just the maximal distance between
any two elements.
Yeah, that's, and then you want to minimize that distance.
I mean, all I was thinking is that if you said that if the only two properties that it needs are symmetry and that it only says 0 when they're identical, then I mean, that has those properties. So I don't really know, but that was just my sort of guess.
Yeah, yeah, I don't know. That's definitely satisfies the properties. I don't know what it would do in terms of yielding an aggregate in the case of of imprecise probabilities. I'm not sure, but there's like I said, there's this gives you an easy way of generating aggregation procedures. A lot of them turn out to be similar or kind of uninteresting, sadly, but they at least satisfy a bunch of desirable properties. But yeah, that's another one to explore.
Kevin, do you want to ask the question about the coherent approximation as well?
Oh yeah, thanks. So just when you were talking about coherent approximation, we were wondering if minimizing the distance or the sum of the distances according to lower provisions would give the same result as minimizing the sum of the distances according to the upper provisions. So does it preference lower provision, or is it, would it be the same?
Yeah, that's interesting. So I have to say, the thing is, I mean, the context that this coherent approximation stuff comes up is, I mean, it's a paper called something like Aggregating Incoherent Agents Who Disagree, and their goal is to like generate a precise probability estimate, and I think they yeah, so I'm not sure. I would suspect that it's going to end up being the same. Well, actually, yeah, because you sum over. So let's find this again. You sum over an agenda A here, right? So it's going to depend on what the agenda is here. If you're summing over a whole algebra, you sum over every element of some algebra of propositions, it's going to be the same because every lower provision is just 1 minus the upper provision for the negation, and the negation is going to be just some other element that you're summing over. So you're going to be able to like do some manipulation and just take a 1 minus outside. And I think, right, but if the agenda is has less structure than the full algebra, I don't know whether they're necessarily going to be the same. But that's an interesting question. I haven't explored that.
Thanks.
Okay, so if are there any more questions? If not, perhaps we can carry on with your slides, Seamus, if you please. Otherwise, and otherwise, whenever you want to stop, we can stop. I mean, we're quite flexible.
Sure. I mean, this is. I mean, these. I put this together so that you have the information rather than that you can. So rather than that we can talk through it. I'll stop in a minute. I'll just say if you do come back to this, or you look at the ISIPTA paper, you have to kind of remember that all of these V's are the lattice theoretic operations, and if you're thinking in terms of like sets of sentences or sets of probabilities, if you're thinking about sets of probabilities, the V corresponds to intersection, and the other one, the wedge, corresponds to union. So they're the wrong way round, if you like, which is just an absolute typo nightmare. Every time I look at these things, I get confused. So that's something to bear in mind, is that basically the lattice is upside down. Yeah, I mean, I won't try and talk through this, but I hope you can see that some of these, like this second one, right? No, not the second one. The third one is basically the if the intersection is non-empty, then the merging has to be equal to the intersection, right? For example. So you can see that some of these principles for merging belief models correspond to Wally's desiderata for imprecise probabilities. The final thing to say is just, there seems to be some kind of little disconnect between the first half I was talking about impossibility, and the second half I didn't really talk about impossibility very much. I didn't mention impossibility. And basically the thing that leaves room for all of these possibility results is that we're no longer requiring that the outcome of the merging operator is a maximal element, right? Remember, we wanted to get out complete and transitive relations. We wanted to get out closed and sort of fully opinionated complete sets of sentences. We wanted to get out a precise probability function. Whereas if we allow sort of less informative aggregation procedures, sort of lower down the lattice, if you like, then, and remember that the impossibility result that we talked about, the sketch proof, relied on the idea that the aggregation has to output something just below the top, right? It has to output something that's really informative. So if we just relax that condition, there's suddenly a whole range of aggregation procedures that we can generate. And then the problem, of course, is, like we saw with just take the convex hull of the union, some of them at least are very uninformative and kind of unhelpful. So then we need to sort of explore that trade-off of like, how informative can we be and still, satisfy these desiderata? And there's lots of work still to be done, lots of exploration still to do. Right, I think I'll stop there if that's okay. Marco, you'll make the slides available to everybody. Did I send you the slides, or I can?
Yeah, send me the updated version of the slides, and I'll put them online.
Great.
Thanks very much. So another round of applause. Thanks very much for your lecture. We're very inspiring, very, very good.
Thank you. Thanks, everybody.
Probably just hear my clapping.
I'm clapping as well.
Thanks so much. And this brings us to a close. Thank you all for coming, and the SIPTA school is over. And it has been quite a journey, a lonely journey for me, at least. I mean, to get everything, from my flat in Liverpool all together. But you guys, showed some warmth for coming and being in the school with us with lots of questions and comments, and it's been heartwarming despite the remoteness of the whole meeting. It has been very nice. So thank you again, and you are free to go now. And hopefully we will see. Actually, I unfortunately probably not then at the conference, the SIPTA conference, but hopefully we'll see you soon at the next SIPTA event. The sooner the better. And if you want to come to visit us in Liverpool when it's possible, do so. We very welcome everyone. And we'll be in touch. So it's been a pleasure. Thank you all again. I'm reading the comments in the chat, so yes, thanks. I think it has been a great, special in many ways, but a great school. So I stopped the recording.